Okay, let's start right from the top. Chapter 1, Basics of Rest Concurrency. And this is sort of like an overview of, it says right here, if you're already familiar with these parts of Rust, feel free to skip ahead, but we're not going to do that because we're going through almost all the book. So let's start. Long before multi-core processors were commonplace, operating systems allowed for a single computer to run many programs concurrently. So this is before threads. What they did was they rapidly switched between processes. Each made a little bit of progress one by one. Nowadays, virtually all computers and our phones and watches all have multiple cores. So they do that with multiple cores now. Operating systems, they isolate processes, so like programs, from each other. So programs all do their own thing, but they're unaware of what the other processors are doing. So you can't access the memory of another process. They're all isolated or communicate. The only way to do that is to ask the operating system's kernel first. But what they can do is they can do threads of execution. So that's inside the same process. And so they're not isolated each other. And how do you do that? You share memory, and this Rust is all about safely sharing data between multiple threads. So that's what this book is about. So there we go. Threads in Rust. So every program starts with exactly one thread. That's the main thread. And one interesting part, you can see that when you do a panic here, just switching to VS Code. Let's open up the terminal. And you can see that if you run this and it panics, you can see, there you go, thread main. So you can see that is the thread mentioned here. So thread main. So there we go. Every program starts with exactly one thread. And can be used to spawn more threads if necessary. And to spawn new threads, we use standard thread spawn. And this is kind of this is actually an interesting example because it uses a function pointer. Usually when you do standard thread spawn, you do you see you'll use a closure here, but you can also use a function pointer, and that's what this is doing, because function pointers implement all the traits, all the closure methods, function fn mute, and fn once, so they can be passed in anywhere. So let's type out this example. You've got this, and then function f. I'm going to put it up here on top instead. And what it's going to do is it's going to print something. I'm just going to print something, and then let id equals thread current, and you can see so that picks up the current thread, and then you can get the ID, and then you can just say let's just change this to some thread, and we can print out the thread ID is, and you do that. Let's just look at this thread ID. I'm kind of curious. It's a non-zero U64. Okay, and it's just getting debugged from the derive attribute. So there we go. Let's go to main. So what did you write here? Hello from the main thread. There we go. So thread spawn, and so we can just stick this f in there instead of doing writing a closure every time. So do that, thread spawn, and then we'll do that again. I'm going to call this some other thread, and then it's going to say hello from the main thread. So this is going to show them working together, and there's no join handle being used, so they're going to the output is going to be different every time. So hello from the main thread. Let's see, let's do it again. Some other thread, the thread ID. There you go. So you can see this time it was a little different. So here we have hello from the main thread, some other thread gives, it says, okay, this is thread ID 2, this is thread ID 3. And so they're not being, there's no join handle being weighted, using join.unwrap. And so it's just when the program ends, then the other threads they just kind of they stop right there. So that's why I use join handles. And all right, so about the thread IDs, yeah, she wrote they're not very useful. So it assigns every thread a unique identifier. It's accessible through thread ID, and there's not much you can do otherwise. Checking, so you can copy it around and you can check for equality. So is this the same thread ID? And there's no guarantee that they will be assigned consecutively, only that they'll be different for each thread. So, all right, not that useful, but they're there. So yeah, you will notice that the output varies between runs. And so here she has some other different output. And what happens, the main thread is done, the process is over, but the spawn threads are still working, but it exits the entire program. So yeah, it got shut down by the main thread. And so there we go. Here is the join handle that we can use to wait around for the threads to finish. So let's type this out. Let's see, where did that go? Function main. Maybe I'll make this a bit bigger. Hold on, I don't want to delete my F function. Okay. Use standard thread like that, and then let T1 equals thread spawn and F, put that in there. And same for T2, and you can see there's the join handle. And then we go hello from the main thread, and then we get these threads to hang around with join, and unwrap that T2.join.unwrap. And so they're guaranteed to finish before the main program is done. And now we're going to have the predictable output. So there you go. So it goes hello from the main thread, and then it goes to T1, and T1 is doing its own thing here, and then we use join to stop it, and then it says some other thread. Then we got thread ID 2, and then it joins the next one, and so it's nice and predictable. We're joining and we're waiting for it to finish. So that's nice. The join method waits until the thread is finished and returns a standard thread result. If the thread did not successfully finish its function because it panicked, this will contain the panic message. So we could, yeah, you could handle that. So that is, that's where it might panic, and that's why we have a unwrap here. So yeah, this is what we did. Running it will know. It'll give you predictable output, and the only thing that still changes is the order. Yeah, that's right, because the let's see, why does that? The only thing that still changes is the order in which the messages are printed. Hello from the main thread, hello from another thread. And that is because, hold on, let's go back to VS Code. Just checking to see if I did it in the same way. Oh, I guess it's because, yeah, the thread IDs are, we're not deciding the thread IDs. So it might one might be spawned before the other one, then it gets 2, and then the other one might get a 3, or it might be the other way around. So there we go. All right, output locking. So the print line macro uses, this is interesting, standard IO, standard out lock, and does that to make sure the output does not get interrupted. And so it waits until any concurrently running expression is finished before writing any output. And if it didn't that, you would get this sort of thing. So it all gets jumbled together. Standard IO, standard out lock. So let's look at that. Standard IO. Let's just get a standard out lock. Let S equals standard IO, standard out lock. Wait. Standard out colon lock. And what does it want here? All right. IO standard out lock. There we go. So not the struct directly, but use standard out to get a standard out, and then lock it, and then we can look at that. Locks the handle. The lock is released when the return lock goes out of scope, and so when it does print line, it does this all without needing to worry about it ourselves. Look at that. This depends on the implementation detail that the underlying reentrant mutex is static. I've never seen a reentrant mutex before. There it is. So it's inside the standard out struct. There should be a line writer, buff writer, blah, blah, blah. All right, so that, let's get back to the book. Back to the book. All right, so yeah, now we are back to the closure thing that I mentioned. Rather than passing the name of a function, as in our example above, it's far more common to pass it a closure. And closures are neat because we can capture values and move them into the thread. So yeah, that's why you usually don't see just function pointers getting passed in. Closures are way more convenient. So let's do that. The example goes like this. Let numbers equals this is like one of my examples. vec123 standard thread spawn, and you do that, give it a closure, and then we can access numbers there. So for n in numbers, we're going to just print out n, and at the very end we're going to join it. So you can join right away, and forgot to move. So we are moving. Oh, actually, I think I was going to mention that we're moving in references, but that's mentioned in the book in a second, so I'll get back to the book first. So there you go. So spawn the thread, and you can just join on unwrap right away instead of saying like let my thread equals da da da. So you can just go join unwrap, and then it's not going to main is not going to finish until it's done. So we're guaranteed to get this these numbers printed out. So let's see. There we go. So ownership of numbers is transferred to the newly spawned thread because we used a move closure, which makes it take ownership. If we had not used it, then it would have captured numbers by reference. Numbers is this the variable named numbers, and that's compiler error because the new thread might outlive that variable, and so you give it ownership, so you won't have that problem. And because a thread might run until the very end of the program's execution, the spawn function has a static lifetime bound on its argument type, so it only accepts functions that may be kept around forever. And I like that point there. May be kept around forever. So sometimes you think of static as being something that like is around for the whole life of the program, but it's more like something that's never going to something that's guaranteed to be around. So it's not necessarily like a starting at compile time thing. It's just something that the compiler doesn't have to worry about being dropped. Closure capturing a local variable by reference may not be kept around forever. Yeah, that's just the same point. So getting a value back out of the thread, that's right. So you can return values from a thread, which is also interesting. So getting a value back out of the thread is done by returning it from the closure. So you just a regular return value. And so you use join and unwrap, and then it'll give you this this output. So let's do that. Let's do that. VS Code. And all right, delete you. Function main. Okay, what are we doing? We're doing vec from iter. Let numbers equals vec from iter. One and up to and including 1000. Vec from iter, and then we are going to start a thread and see right now T is a you can see it's a join handle, and a join handle, it's got this it's a T. This is the return value, and usually usually you don't see people return from threads, but you can, and when you're not returning anything, you'll just get the empty tuple there. So standard thread spawn move, and what are we doing? We're going to get the length, let len equals numbers dot len. So we got that, then we're going to sum them, I guess. Numbers dot iter dot sum, and when you sum, you have to be specific about what you're going to, what the integer type is going to be. If you don't, then it tells you consider giving sum an explicit type. And of course, you could always say like that. What you can do, sum usize. And then finally, sum.len, and the moment we do this, then the join handle changes to a join handle of usize. And then what are we doing? Let average equals t, and this is a join, so we have to unwrap if we want to get the value, and finally that gives us the usize, and then we do that. Average is, and then we do average. I like how this book starts out nice and readable. Like if you know the Rust book, then this is all very followable, if that's a word. So there you go. Average is 500. So let's get back to that. Let's see, anything I didn't mention. Here, the value returned by the thread's closure is sent back to the main thread. If numbers had been empty, the thread would have panicked while trying to divide by 0, and join would have returned that panic message instead, causing the main thread to panic too. Let's do that. Let's make that happen. So let's divide by 0. So instead of sum, we're going to do sum divided by 0, and then here we're going to sum divided by 0. Yeah, we don't need length anymore. That's fine. Let's see. Compiler's too smart. This operation will panic at runtime. All right, I'm just going to, all right, panic. What do you think of that? There we go. So the thread panics and we get explicit panic, but the main thread is still doing its thing. So it gets this average is any. Oh, that's right. This is what I did in my recent video with the, I think this is the, what is it? What's it called? The panic info. Boxstein ND. Okay, let's try if let air e equals average. Let's e dot downcast ref stir. Did it downcast? See if that works. Yes. I'm going to move this up so you can see it. So there you go. Did downcast. Yes, we got sum, we got explicit panic. So that is the, this was in a video of mine just, 2 days ago about having a panic handler. You get this panic info struct, and then you can, this is kind of like the same thing. It's the payload, and it's a dyn any, and so you can use downcast to turn it into a concrete type, and most of the time it's going to be a stir, and that's your panic info. Okay, so right. Oh yeah, I read this yesterday. This is interesting. Thread builder. So the standard thread spawn function is actually just a convenient shorthand for standard thread builder, new, spawn, unwrap. Interesting. There's an unwrap inside there, but it's probably guaranteed to happen. So standard thread builder allows you to set some settings before spawning it. You can configure the stack size for the new thread and to give the new thread a name. Standard thread current dot name, so that's like main or whatever, and will be visible in monitoring and debugging tools. So we should do that. It also returns results because it might run out of memory or resource limits have been applied to your program. Whereas standard thread spawn simply panics if it's unable to start a new thread. So I've never seen a thread unable to spawn before. All right, so let's do that thread builder thing. Standard thread builder new spawn unwrap. So let my thread equals standard thread builder new. Yeah, builder new dot spawn dot unwrap. Let's get rid of this. Standard threads new spawn thread builder new spawn. And it wants a closure, right? There we go. And then new, so I think this is where we can give it a name, right? Nice thread. What's it? Should be a string. Okay, now you're a string. And then, so if I panic there, there we go. Thread, nice thread, panicked at explicit panic. So that worked very well. Let's see if the thread builder has anything else that's interesting. All right, builder. What do we have? We have new, builder, name, give it a string, gives it a name, stack size. I wonder what the normal stack size is. What else do we have? Spawn. Spawn unchecked. Let's see if we can see what the general stack size is. Pass the desired stack size to rest min stack. The default stack size is platform dependent and subject to change. Currently it is 2 megabytes on all tier 1 platforms. There we go, 2 megabytes. So that I think will be good enough for a first video. And next up is going to be scope threads. So see you then.